Hello, everyone. Our second speaker is Halley Fritze. She is PhD student from the University of Oregon. Her talk is Topological Exploration through Higher Dimensional Mapper Graphs. Please go ahead, Halley.
Yes, thank you. So this is sort of my thesis work, and my advisor is Dave Sinha at the University of Oregon. I forgot to write him down, but yeah, all right. So a little bit for today is a lot of my work is based on this higher dimensional construction of mapper. So we'll first introduce what that is and how it is used. Then we'll introduce the concept of two-mapper, and then we'll look into some mapper applications that I have sort of gauged towards climate science. Yeah, so first, before I get to mapper, I want to first introduce sort of the basis of my subfield, which is topological data analysis and the construction known as the nerve. So if I have a finite collection of sets U, we can define the nerve as the simplicial complex whose vertex set is just the index set of the cover. So you just take all of your open sets, you contract them to vertices, and then you have a simplex in your nerve if and only if the intersection of all of those cover sets defined as the simplex is non-empty. So this is how you can sort of take these like finite covers and construct simplicial complexes from them. So for example, if I have the circle, right, I can cover it with this cover that I've chosen, U1 and U0. So I'm just covering the northern hemisphere and southern hemisphere of S1. And if I take the nerve of that cover, right, so U0 will collapse into a vertex, U1 will also collapse into a vertex. And because their intersections are non-empty, I connect it with an edge. Cool. So the nerve kind of is the main construction, even if you study the other variants of topological data analysis, everything happens to be a nerve. And it's all because of this really wonderful lemma called the nerve lemma, which says, so if I have a metric space and I take a finite cover on that metric space, if every non-empty intersection of open sets from this finite cover happens to be contractible, then the nerve itself, if I geometrically realize it on my metric space, it's homotopy equivalent to the original space. So that just means I can cover a metric space, and if the cover is good, right, its nerve is homotopy equivalent to my original space. And that's just absolutely wonderful. So let's go back to this example, right? We'll notice that, clearly I'm starting with a circle, and I do have a finite cover, but U0 and U1, right, their intersection is not contractible because their intersection happens to be, this little part of S1 right here, as well as this little part of S1 right here. So it's not contractible. And we can also see that the nerve of this cover, right, is a line, not homotopy equivalent to the circle. So if I pick a different cover, for instance, this V0, V1, V2 cover, right now, if I check all my pairwise intersection conditions, right, V0 and V2, their intersection is contractible, V0 and V1's intersection is contractible, and V1 and V2's intersection is contractible. And thus
Is
I
this
have...
an if and only if?
It's not.
Okay.
That's a good question, though. But I do have, if I have this sort of cover, then I get a simplicial complex whose nerve is, or the nerve is homotopy equivalent to my original space. Yeah, so, right, nerves are cool. They're like the best thing ever. And that's sort of the basis of the construction of not just mapper, but the other things in topological data analysis. But today I'll be talking about mapper. So mapper, what is that? It happens to be this soft clustering algorithm, which takes my data set and constructs a graph out of it. So for instance, if I have a topological space, or maybe some discretization of a topological space, but call it X, we just have to choose some parameters. So I'll choose a filter F. It should just be some continuous function from my space to Rn. For here, I just have the height function on the torus. It's continuous function to R. I then am going to choose a cover on the image of my space. So I'm going to cover the image of this torus on the real line with these cover sets, U1, U2, U3, U4. They're just intersecting intervals. Then from there, what we do is for all the data in the open set on this image, we're going to pull it back into my original space. And we're going to have some clustering algorithm determine whether or not, like, how many connected components should that pullback be. In the case where X is a topological space, there is no clustering algorithm, right? You just do this verbatim, but in a data set sort of context, you need a clustering algorithm to determine how many connected components should this pullback be. Okay, so it sort of subdivides my original data set into these clusters, and then I take the nerve on those clusters, and that was what gives me the mapper graph. In particular, the mapper graph here is just the vertices and edges. It's the one-dimensional skeleton of the nerve. I don't care about any higher dimensional information. Okay, so yeah, from here I can sort of get some topological approximation of a graph or of a data set. In a more clear context example, let me give you an actual data set on a torus and not a torus. So this data is embedded in R3, right? Instead of taking a height function, let's just do like an R2 coordinate projection into the plane of my space. And let's cover it instead of uniform intervals. In R2, these would be overlapping squares. So I get this slightly overlapping checkerboard. These are my open sets. And then when I pull them back and take the nerve, I'm going to choose a clustering algorithm. The standard one to choose is dbScan, if you know what that is. If you don't, it's just one of the better clustering algorithms that exists in sklearn. And that's what gets me some sort of the mapper graph. So it gives me some graphical representation of this data set. Okay, so mapper has a lot of applications too that I'll mention. I don't have them in slides, but it's been used successfully in like breast cancer studies, malaria studies, basketball statistics. Political science has some really interesting examples as well as it's been used to like study the spread of infectious diseases, including COVID. So it's really good at giving sort of the connectivity of a data set while still being able to sort of cluster it. But so what I was interested in is the fact that if I take my cover, right, here it's 4 squares, right? Of course, I can make edges just by pairwise intersections of cover sets, but when I have like a 2-dimensional cover, right, in this case, I have a lot of higher dimensional or higher fold intersections of this cover. So, right, this intersectional structure should yield a higher dimensional nerve. So for instance, like the top 2 squares overlap with the bottom right square, or the bottom left square. So that's a 3-fold intersection. It's non-empty because there's data in this little tiny square. So I should be able to fill that in with a 2 simplex. And then similarly with the top 2 and the bottom right, all of these 3-fold intersections are non-empty because all 4 of them are non-empty. So I should be able to just fill in these 2 simplices because that's the definition of what the nerve is. And so taking this into account, we sort of believed that this is sort of giving us a better manifold approximation of point clouds, as well as can help us decipher like the density of these sort of spatial approximations through this like higher dimensional nerve. And so using this, we sort of defined this object as 2-mapper. So it's just, what is it? It's just taking a mapper graph. So you'll have your point cloud, choose your filter function, choose your cover and choose your clustering algorithm. Then instead of taking the 1-dimensional nerve and getting the mapper graph, just define the 2-dimensional nerve and you get the 2-mapper graph. So for instance, on this original example I showed you, right, we have the 1-mapper graph. However, there's lots of data and all the tiny 4-fold intersection parts. So we should be filling all of those simplices in and getting the 2-mapper graph. And so the sort of advantages of this thing is now, right, you can more clearly to see where like the significant cycles and holes of your graph are defined. And that can help you out sort of with, you know, identifying higher dimensional holes. Additionally, mapper graph was just an original graph. However, now that it's a 2-dimensional simplicial complex, I can make some accurate like approximation of Betty 1. Instead of just saying, well, it's connected and it has these many connected components, which is typically when you use mapper, it's in an exploratory setting and you're just really catching like connectedness, not trying to like approximate Betty 1. So this is sort of our take on trying to approximate Betty 1. And so I kind of took this idea and I went to this conference this summer on topological data analysis with applications towards like dynamical systems and climate science. And from there, I kind of have been toying around and working with collaborators on constructing ways I could use 2Mapper to sort of think about applying it to climate regimes. So before I get to how I do that, let's just dive in a little bit onto climate regimes. So what these could be is you could think about, when I say the word climate regime, it's sort of a not completely deciphered language in the literature, but you should just think of it as some like atmospheric circulation on the Earth. So toy models of climate regimes sort of include the following things. The Lorentz 63 double butterfly dynamical system is an accurate toy model for a climate regime. Something else is the Charny-Devore dynamical system. I believe this one sort of models barocentric pressure in climate systems. So these are two toy models. They're dynamical systems, right? We can see like the Lorentz 63 has two very significant cycles. And so maybe we should use topological data analysis to like identify those cycles. And so there was previous work done to do this using this technique called persistence homology, which just instead of doing the mapper construction, they construct a simplicial complex through taking the nerve of expanding balls over time, and that gets you an object you can study. But the problem with this happened to be that if you let the dynamical system, which is inherently chaotic because we're studying climate systems, if you let it run forever, the density of the point cloud gets so dense that you end up losing topological features. So you can't necessarily easily identify two cycles in this system if you let it run for a million time steps. And so what they had to end up doing was sort of piecemealing their data set via like a density estimator, and then computing where the cycles are over also a filtration of density. And so they get this object where you can say like at the 60% threshold, we had one loop, right? We can see it right here in figure C. And we had one connected component. At the 80% column, right, I have two distinct loops, and we can see that at the 80% threshold in figure B. However, while this is nice and visually good, the theory states that it's really hard to tell that there's no actual guarantee that this loop on the 60% threshold is the exact same loop coming from the 70% threshold. That's actually not theoretically guaranteed, and it's recent work has started popping up to sort of address this question and this problem, but the problem is this multi-parameter filtration is a very non-trivial object to work with, and that's really difficult. So I tried to think about how I could do 2Mapper for this to give us a better estimation for that. And so I was working with something, and we decided to think of a way to use Mapper to apply to climate systems. And so we decided to do it with this thing called temporal mapper. So if you have a data set and it's some dynamical system, you can think of each point as both a spatial part, like has a spatial portion x sub k, and then a temporal portion t sub k. So right, it's a dynamical system, there's a temporal feature, so we should extract that. Now, if you take your data set and you construct a mapper graph on it, right, every data point still has some temporal feature, and so we're going to extract out that information, and from that construct a directed subgraph whose edges sort of witness this temporal feature. So what do I mean here? I mean, I have a mapper graph. Remember, the mapper graph is just the nerve of some pullback of a cover, and that cover contains data points. So if I have some data point, x sub k, t sub k, in one portion of my cover, and then in the next cover that is connected by it with an edge, there's the t k plus 1 point in the one connected by the edge. Well, right, that means that edge witnessed some transition in time between this point to this point as the dynamical system worked. So if I sort of apply this construction in theory to every edge in the mapper graph, I can construct some directed subgraph of my original mapper graph that is showing like how the dynamical system is working and running. Okay, so this was sort of the construction. It's not trivial to do, and a lot of this I had to code by hand, and I worked on this with a lot of the toy models and got some interesting results. And I decided to throw them all out for time, and we'll just go to the actual real world example that I worked on for this, which is the Madden-Julian oscillation, which you can see on your right. So what we wanted to do with temporal mapper was sort of ask or try to answer the questions like, what are typical dynamical orbits or other patterns of behavior that are occurring in the dynamical system? And can we visualize these or approximate these orbits using temporal mapper, right? If you think of mapper as sort of like an approximation of your data set through some like simplicial complex or graph complex, you know, can we sort of take all the general information of the dynamical system and sort of approximate the orbits through this directed subgraph? And so we're going to be doing that on the following data set on the right, which is very messy. Okay, so that data set is called the Madden-Julian oscillation. What it is in life is it's an eastward moving pulse of cloud and rainfall. Near the equator, it typically occurs every 30 to 60 days. So what happens is it's on It's on the eastern coast of Africa. It starts to move across Indonesia and northern Australia, and then it sort of kicks itself into the Pacific. And some climate scientists, I believe, argue that it also sort of has some influence on El Nino. So it's this large pulse of cloud. It goes from East Africa to the Pacific every 30 to 60 days. This sort of cycle happens. And so how they decided to measure this sort of oscillational process is they measure it in this two-dimensional phase space where they take a lot of the features of the data set, and then they also place it on this sort of radial space where each sector is some area of the Earth. So we can see in 7 and 6, so I'm in the Western Pacific. Here I'm in the Western Hemisphere in Africa in 1 and 8. The Indian Ocean is 2 and 3, and the Maritime Continent is 4 and 5. Maritime Continent meaning like Indonesia and Northern Australia. Had to learn that one. But pretty much what happens is over time, it just sort of does this like anti-clockwise movement. And the colors here are just what month it is for the data set. So this updates every day on a website, which is really fun. So you can sort of track it in real time. And that's great. And we can see it sort of like oscillates counterclockwise. But what happens when we take 10 years worth of that data, which is actually only 3,500 points approximately, right? However, it's a very dense set.
Sorry.
Yeah.
Quick question.
Yeah,
what are the axes here?
RMM1 and RMM2, the axes here, so these are the computations based on the construction that the climate scientists have used to put it in this like two-dimensional phase space. So there's some combination of feature parameters like barometric pressure, velocity, like wind velocity, all of the weather data that they collect. Yeah. Yeah, so they do a pre-process on all the data to throw it on these axes. But I will say the radial or the angle locations of where the points are laying has to also do spatially. How far out they are from the origin center is based on a lot of those like feature computations. How strong the MJO is. And for instance, the stronger the MJO is, the further away from the origin it is.
Do you know if this oscillation is related to like Kelvin-Helmholtz instability or something?
I have no idea what that is, so no.
Okay, then ignore the question then.
No, that's okay. It's interesting. I'm definitely not a climate scientist, and I don't really work with dynamical systems too much at all, except for in this sort of example. But I wonder if my collaborator would know. I bet he would. Right. So the thing about this data set is too, with it not being a toy set, is it's very dense. And it's so dense, right, that you can't see like any cycle admitted on it at all, right? There's no distinct hole to look at and see, yes, that this dynamical system has a hole in some behavior. So even the other field of persistent homology, like applied to this phase space, like wouldn't be able to identify any cyclic behavior. But how I could do this with 2-mapper is sort of in the following way. I actually had to construct a different cover type for this that doesn't exist in the program or any of the Python programs, so I had to build it myself. And so to kind of extract the fact that this phase space was like wedged radially, how I defined this cover was, we're going to take our cover set, and it's just going to be these pi/4 angular wedges of the bounding circle. And then we're going to radially subdivide these wedges into annular regions so that they overlap like this. So let this be my cover set for this data. And then we're going to make and construct TwoMapper on it with the following parameters in the corner. So I'm going to take the wedge cover. I'm going to take pi/4 angular wedges. I'm going to let them overlap by about 10%. And what I get for TwoMapper is the following object. Okay, so it's mostly cylindrical, and all of the simplices end up being filled in. What I can tell you is that the cylinder near the origin is the bottom of the cylinder, and then as I spiral out with these top things, these are the frays of the edge of the Madden-Julian oscillation. Okay, so that's the TwoMapper graph that I want to do temporal mapper on. I've removed all the two simplices just so it's easier to see. And then I look for, I construct its directed subgraph. This happens to be the directed subgraph. And because it's a directed subgraph, right, I can extract paths on this space. And so I can take and compute these paths on this directed subgraph. And from there, we can say, well, this is likely an approximate trajectory for this dynamical system is it follows somewhere on this path. And what's cool about Mapper, right, is all of the vertices contain some subset of data points. And so on this path, I can extract all of the data that exists in this path and regraph it onto the dynamical system. And so you can see starting at cover 0 in this really bright yellow, it's sort of anti-clockwise spirals outward towards the end of the boundary, and then it sort of comes back in this like dark purple. It's a little tricky to see, so I made a GIF of it so you can see exactly temporally where are the data points going as I traverse this cover space. So it's just all the data that's traversing along of this path on the left. And so from here, we can say, well, this is an approximate temporal trajectory for this dynamical system. Starting at this bottom vertex here, I did have to declare a start point, so that was a choice that I made, and then from there it computes this path. And so what we decided to do with it afterwards was, great, it's a collection of data points. Obviously, they're not all temporally collected. It's some approximation via some collection of data points. So I then had to ask, like, okay, but how many data points in this subcontainment subset of data are actually connected in time? And it's the following line that we have here. It happened to be November in 2021 up through January of 2022, which is about a 3-month period, which is equivalent to about approximately 1 Madden-Julian oscillation. So right, it starts right here in the bottom left, and it sort of traverses up and over. And you can see that this Madden-Julian oscillation in particular was quite noisy, right? It sort of circled in on itself a few times up here. So it's not very easy to sort of feel out, but it is something that we can connect, sort of detect with Mapper. And it was a really fun sort of project to think about. So I forgot, do I have conclusions? Yes, I do. Great. So yeah, what did we sort of think about today is sort of using a higher dimensional topological application of Mapper to identify these higher dimensional simplices, which we can observe higher dimensional densities and extract more features out of data, is sort of what I like to think about. Additionally, something that I didn't get to, but my work in my thesis also kind of pairs on is cover types and studying what cover types work best with Mapper, and trying to prove their stability with respect to interesting parameters. But most certainly, using this as an application for real data to sort of approximate trajectories and climate regimes is something that I'm still interested in working on with more non-trivial examples than the Madden-Julian oscillation. And yeah, I think it was a good time. So yeah, thanks for being here. Thanks for having me.